All right, yeah, welcome back. In continuation with our course, we are continuing from where we stopped. Last time we looked at a simple and a multiple linear regression, whereby we have a variable compares with other variables linearly, and where a variable is dependent on other variable, we have association of two variables or more, and also interaction of variables. Okay, so especially independent variables. Now we want to look at logistic regression, and not unlike linear regression, the dependent variable in logistic regression is binary in nature. Okay, binary means value is either 0 or 1, true or false, yes or no, and which is also based on probability. All right, from the chart here, you can see that this is the curve of this is how the curve look like. This is how it looks like. This curve of regression, and this is a yes or no target variable, or we call it a independent variable, yes or no. So which is y-axis. So the y-axis is divided into two sections, into two equal half. Okay, so which is this side from 0 to 1, then half is 0.5. That is how registration operates. Then this particular line, which is the threshold, anything above this line is positive, anything down this line is negative. All right, so let's say we have work experience in years, and we have a probability of being a staff being promoted. All right, so the promotion or the probability of being promoted is dependent on the work experience of the staff. So the higher the work experience, probably the better the higher the probability of being promoted. So this is the core of how it goes. So the part will be yes or other no. So when it is anything, any value 0.5 downward means it is no, and any value 0.5 upward, it means yes. So that is how registration is covered, or it operates. So we're going to stick to that, look at that practically using R as usual. So let's go and look at how we can code this in R Studio. All right, so the code snippet we want to focus on here perform logistic regression, and here the goal is to predict the probability of someone being diabetes positive based on multiple clinical variables. We have multiple clinical variables I want to look at. I want to predict the probability of somebody being diabetes positive. All right, so let's load some packages we are going to use first. We have to load these packages. All right, these libraries, we load them. This is just for, this one is just for to visualize our chart later. So I just look at this, so just load it together, never mind. All right, so it's loaded. So now we're going to be using this data set called diabetes. Okay, it's inbuilt, actually it's inbuilt, and from this particular data set, so I have to bring it out so that you can use it. So this particular data set, diabetes, all right, so I load it into the memory. Then let's first summarize it and see how it look like. Summarize the data set. All right, we summarize it now. We look at a data set. It has a following: pregnant, glucose, pressure, triceps, insulin, mass, pedigree, age, diabetes. This is our target variable. But you can see that it has some what they call it. It has some missing values here. You can see these are 5 missing value. This 135 missing value. You can see that this one 277 missing value. There are so many missing value here, so we can just, for now, actually, of course, we understand how to handle missing value for now, so we can imputate the missing value, but I just want to omit the missing value for now. I can just omit it for now. So let's just pass so that we can quickly experiment our work before we go further. So let's just omit the missing value for now. So you can also glimpse, this is what we have there. You can see. So when we glimpse, we have a total number of rows. We have this all the sample data inside here for each of them. Okay, this is our diabetes, our predictive variable. This is our target variable. All right, positive, negative, positive, negative. All right, we want to know if the person is diabetes positive. So let's omit the data first. Let's omit. Right, we omit the end variable. Then we summarize again. Okay, we summarize again. So we have eliminated all the missing values now. So all right, so no more missing value in this data set anymore. So we just what we just do that we omit all missing value. That's all. So all right, so we don't need to waste our time on that. So we can, but for you, just go ahead and input input a missing value using our usual past concept we have learned before. All right, so please go ahead and do that. That will be easier, so not to waste time here. So now we have to split the data set now. All right, before we split data set, we need to first we need to work on the factor variable, which is number 9. The factor variable now is called diabetes. In diabetes now, it's negative in value. I mean, it is a character base, negative, positive. So we want to make it 0 and 1. So what we do now, we call the data, and then we in the column, ninth column, this ninth column, diabetes ninth column, then we use S apply for the ninth column, and we switch, make anywhere it is negative, make it 0, positive, make it 1. So that's what we do now for the ninth one, which is a ninth column, right? So we can run that line now. It's done. So if you check again, if you check briefly, you see that this derivative is positive and negative. So if you glimpse again now, let's glimpse again and see what I'm talking about. If we glimpse now, right, data, our current data, so that you can see that the diabetes is now what, 0, 1. Okay, why? Because we have changed it to 0 and 1. Then we can now split our data now so properly. So let's split now. So this one should not be splitting. So it should be call it a changing factor variable, or let's call it target variable to 0 and 1. Excuse me. All right, so let's now split our data set now into 70%. Now this area of splitting, now we want to split the data set to 70% training data and 30% testing data. So in this splitting, we have training and testing. So we have training and testing data now. So if you say set seed now, what we are doing that we want to split data set into, this is our data set called data. We want to split into 2. All right, call 70%. This 0.7 means 70% training. So and the remaining one will be testing, which is 30%. All right, so we now say our training data is a subset of this data set now, of this split, which is what, true, which is 70%, and the testing is now split, the remaining one, which is split, it will be what is called 30%. So we have here we have a 70%. Let's say we have 70%. Okay, here we have 30%. All right, so that is what we did just now. So this is a common way of training and testing. This common way of learning, both in R and Python, and using other algorithms. We are going to be following the same concept, all right, of data splitting. So there are many ways of splitting our data. You can create partitions, you can do other things, so but at least this one is easy and it's faster. So let's fix our model. Our model is using GLM. Don't forget the former one we did just LM linear model, but this one is generalized linear model. So we are going to just fit our model. Don't forget, the first thing you need to look at is called the target variable, diabetes. All right. So we are using dot here because you want all data, all the remaining data variables to be passed into it. All right. That's the meaning of a dot here. So if you don't want all, if you want to select few, you can just remove dot and just enter the data, the columns one by one, and plus it like that. Our data set is training. Don't forget this is the training data set, right? Training. So then the family is binomial. This family is binomial. That's what we are trying to do. It is a binary concept. So we run this model, right? We run the model. So now we want to look at the model performance first by looking at the summary for each of the look at it here. So this is the model. So we have coefficients here. This as usual, we have intercept, right, and estimate. So looking at this p value, you can see that you have to ignore this line. This intercept line. We start from the variable lines, which is pregnancy. All right, pregnancy 0.045. Not well, you can say significant because 0.04. If you approximate this to 5, it won't be significant anymore because it's already more than 0.5. Right. So and the key word, the point is that it must be less than 0.05. So glucose is significant, right? Glucose. Then we also have insulin. Also is contributing to the diabetes. We also have a the mass of the person participant. We also have the pedigree of the person. Pedigree is also significant. That is all that is significant here. Okay. So this one showing that this one is highly significant, followed by this two asterisk, followed by this, all right, one. So that is just a sign we are showing here. So you can see it's a sample here. All right. So now that we have seen this, now we can now go ahead and predict. All right. So we can predict. Though we can filter some columns that are not necessary, or maybe they're not contributing much to the accuracy or to the prediction. We can filter them off out. All right. But you need to do that carefully. All right. Because sometimes it may not be contributing much here, but they have they will be significant. I mean, they be important to the accuracy in predicting the accuracy of the model. All right. So let's make a prediction here because of say probability. This is just a concept. We just create this object, and then we call it, we pipe our model in. So our model we have created here just now, this is our model. So we pipe it in here. All right, we call predict function. We pass our testing. So we want to show the testing. We can show the training first before the testing anyway, but just want to show the testing because that is what is important now. Because we want to tell, we want to do the test, see the testing. We have already created the model already, which consider as a training. So now despite our type is response. All right, this testing is what is our testing data, which we created here already. Okay, this one, our testing data. So now when we run that, if we run this line, okay, then we can make a prediction. We can predict the class. This is another function, object we created now. We can call it predicted or whatever I want to call it. So we want to say now this is our major area file because this one is saying that if else probability, this probability we have predicted, we have created is greater than 0.5, then 1, else 0. That is what I showed just in the slide just now. All right, that what divide the curve into two, make the some part positive and the downward a negative. That is threshold now. Okay, so if that is done, let's run that line and see. All right, good. Then we can now go ahead and do the confirmation matrix. All right, so that we pass our test that diabetes here. Okay, our what do you call it now? Our target variable here. Then predicted class we have done here. We pass it to the matrix to see so that you can do our accuracy. Then that is done. Then we can now go ahead and configure the accuracy. Accuracy is equal to mean predicted class. So we pass we want to look at the mean of this predicted class now. Okay, which equals to testing diabetes. So this line, we run this line. All right, so we can now print accuracy now. All right. Okay. So we have not printed our function matrix, which is this one. We can print it also. Let's see. This is our function matrix. Okay. And this accuracy 0.7938. That is 79.4%. So that is what we're able to get, 79.4%, which is our accuracy. All right. So we can also look at the plot of the curve. Now, looking at our result here, you see that the only one that has a highest physical nature available here is the glucose. All right. So it means it will demonstrate a better chart for us. It will be able to show us a better curve of that logistic regression. So we can go ahead and we can also plot a curve of others as well, but they will not give us a better curve. Why? Because they are not properly. You can see that they are not contributing much. The relationship between the diabetes and each variables will determine how the curve will look like. So if you, for example, plot the curve for diabetes against, let's say insulin just 0.45, you can see. Let's see what I'm talking about. Insulin. If you run this line, okay, you see the curve. Let's say the curve. Look at the curve. This curve. You know, the curve is not that coming out much. You can see. So this is our data. Our data here. So the curve should come out like this. So it's a positive curve, but we can do it for others. Well, let's do for glucose. Glucose. The reason is because glucose has high variability. Okay, and you can see an high significant nature here. Okay, so this is a positive estimate and also 0.09000. Okay, which means highly significant here. So then you can also put for pedigree, which we also use. Okay, let's try for pedigree also. That will be a little bit better than insulin. All right, because that is more significant than insulin. So you can try that also. Let's run. You can see the curve is better than insulin. You can see it's coming now. So let's now do for glucose now. So glucose against diabetes. All right. You can see this curve is coming out clear. Can you see? All right. You can also look at the error by making this error true. All right. You can see that you can look at the. So let's make it true. You can see here. So the more we go up to the above the threshold, all right, the more the error standard error is. Right. So we can undo that. Let's remove the error. So we don't need it actually. So just to see. So now this is our curve. Okay, so this is our curve, so we can view it properly. Yes, this is curve, and this is what was shown before here. You can see this is what was shown here. So this middle here now is 0.5, and down here means no. That means yes. So this means negative. This means positive. That's what it means, right? So anything above this positive and negative. So we go back now, we see that here also we have 0.5 here. Can you see 0.5 for diabetes? Is y-axis. Then we have glucose here, x-axis. So glucose is contributing. That means the higher the glucose consumption, the more the person the probability of having a diabetes. All right. So this is a threshold here. Okay, in between here. The line is not shown, but at least you can see 4.5 here in the graph here. So that this is our plot. You can label it and use it for your analysis. So that is that for logistic regression. Okay, so both the accuracy that we have predicted and also the data that we have shown here, accuracy, I mean, of the p-value here, they are very important. So you can note them. Well, for glucose, which means glucose has a higher probability of somebody being diabetes. So that is what we just concluded. So thank you for listening. We will proceed to other area of supervised learning in the next class. Thank you. See you later.